about satellite data for monitoring and do it for analytical models. For some reason, I know nothing about Scala, and the stack for our company is slightly different, but still we have the same challenges. The main problem for us is how to process this massive amount of data at scale. So the satellite imagery is really cool. You can persistently monitor any location with different sources of data and see the change. So for example, the image behind me is not a static picture taken from one satellite shot. It's actually encoded time series of images. So for every pixel, we tracked how the behavior looked like through agricultural season. And this is cornfields for Iowa. And for the areas colored with the same color, we can confidently say that these areas were they were harvested at the same moment, which means that it's the same crop, and also it's very likely to be the same farmer who ordered the machinery to send for a certain location. So having insights like this, just purely on satellite data without any knowledge about what actually is going there, like without any reference data, allows us to do the monitoring and get decisions and share these decisions with different stakeholders who would potentially be interested in this data. But the main problem here that the dataset we're currently talking about is 5 to 6 petabytes, and the challenge here is how to effectively access this data. So what our company is doing, we are building an API and a platform for easy access to the data, because not so many people need a really global access. Everyone is interested in certain locations which the business is actually happening. So what we are building is the archive of data and the processing pipeline that goes and looks specifically for the area of interest for the users, and we process this data and distribute to the users through the API, which can be easily visualized or downloaded or be used in analytical models on the user side. So as I said, the first part of it is a monitoring. We pool all the available data from different sources, including our own constellation our company is building and the public domain data. Then the analytics starts. So the first cool thing is the measurement. We have not only the current observations, but also about 20 years of monitoring, and we can confidently know that how the pixel behavior looked like this year, many previous years, and expect how it should look like for the next years. So comparing this pattern with the ongoing observations, we can track changes and tell whether there is some unexpected activity or off-pattern activity is happening. And with this data, it's possible to manage to require for more high-resolution data or take actions. So from these 3 steps, basically, the Astro Digital vision builds in. So first to the data. So just to get a sense of how the satellite images looks. Usually we are talking about the satellites which fly on the low orbits following the sun, so solar synchronous orbits. So it's like a cloud of different satellites following the sun, and they take shots. So the typical shot is 200 by 200 kilometers, and the spatial resolution is 10 to 30 meters in 1 pixel. Comparing to, for example, Google Maps, it's not a super exciting resolution, but still, if you have a consistent image daily for the entire landmass, it's really a valuable data source, maybe not only for visual assessment, but also for analytical models when we compare the previous day or the previous year with current year, and can measure the change or track the same pattern activity. Let me give you examples of how the typical imagery looks like. So Landsat 8 is the NASA satellite launched in 2013, which makes the resolution of 30 meters. And it has 9 spectral bands. It images the entire landmass every 16 days, so it's typically 2 images per month. And plus it has the previous generation of Landsat 7, who has archive of 18 years in addition to that, with the same spectral parameters. European Space Agency launched the Sentinel II satellites, and their archive starts in 2015, and it's 10 times more high resolution because it is 10 meters in 1 pixel, and the temporal resolution is every 10 days, so we have a shot for every 10 days. And combining these 2 guys, they allow us monitoring every 4 days, which is almost like 2 shots per week. But effectively, it's not enough, especially for cloudy regions, because the problem with multispectral imagery is that it cannot look through the clouds. So what we want to do is to make shots as frequent as possible, ideally every day, or maybe several times a day, to increase the chance of having a cloudless image, or, for example, to fuse several data sets in order to cover the pixels which were under clouds with one image with the pixels from another image. So overall, it would generate us something like this. So this is a multispectral image of the Vegetation Index. And by the same color, again, we see the areas with the same type of crop in the same phenological stage or the same phase of growing. So I compared this data set with the map of vegetation from USDA, and for that specific location, there were tomatoes growing that year. And by comparing the tomatoes with neighbor field or with tomatoes previous year, we can say that maybe there's an evidence of some disease there. But this is more about the visual assessment, because what we want to do is to go beyond pretty pictures and be able to have the measurable analysis to do some more interesting stuff. So for example, the building detection. So here is Dubai, and the red dots are the images which were labeled to be newly created buildings. And the green dots are the images that were suspects to be buildings done by the classification. Why we use Dubai? First of all, because the building process is really active, and secondly, because it's really a cloudless region. So it was a successful project for us, and for the green dots, they were proven to be suspects to be buildings, and specifically for that area, the only work which was supposed to do is only to draw a more precise lines around these buildings, but actually the fact that something is being built there was proven by this type of imagery. So if we look more precisely in how this type of operation was done, we can see that there was like a small area, like a small window was extracted and taken from a series of images. Actually, there were 50 images used. Then we pixel-wise look at the spectral behavior for every location and detect areas which show the behavior which looks similar to newly buildings. So in the bottom image, these areas were highlighted by purple, and we can confidently say that for all the purple areas, we see that they are the buildings which were appeared through this period of actually 2 years. So yes, we detected these images which were built in 2 years. And such type of analysis can be done globally for the entire landmass, which is for our constellation of satellites is 15 million square kilometers. This is a really heavy computational problem because it means to process over 200 million images per year. And if we look at the typical satellite shot, we can see that it is like 3 spectral bands, and we have this amount of pixels to process. Processing of one scene took 30 seconds. So if you take a typical, I don't know, on my laptop, the processing of this just a daily data set would took 17 years. But the real problem with this data is that the human activity and the areas of interest which are interesting to humans is not equally distributed over the landmass. We really need less than 1% of data to be processed. But the question is what exactly the location are needed and how to process these locations cheap, effectively, and really quickly, because another problem is that for many applications the data should be delivered really quickly. So for example, for hedge fund, for trading, the data is required the same day, so like 8 hours window, including the time to downlink the data. So effectively for the processing of data, we have hours, maybe minutes. So what can we do? Specifically for our case, we introduced the window-based read architecture for AWS Lambdas. So what we did, we defined a problem, an analytical model to be processed, define the size of the window and the depth of the archive to look at. We feed this to a required number of AWS Lambdas and perform their analysis. So this, let me go a little bit deeper of how it looks like. So we don't download or process the full scene because it's like a 1 gigabyte archive per just one data point, while we need to observe thousands of them. So what we do is that we send a specifically bounding box around the area of interest for their location to be processed. And in percent, it's like 1% of the image, or maybe less. So we work only with this small chunk of data. And for that, the limitations for AWS implementation, which is about 1.5 gigabyte of RAM and 500 megabytes of memory of storage, is enough to do the process. And another cool thing that we can do it in parallel. And the most important part is that the satellite archives, they are distributed within the different data centers. So we can locate these Lambda functions in the same data center as the data is located. So having this, we don't waste too much time on sending the data from one data storage to another, and it's really a good idea to have the processing capacity near to the data to optimize the cost for sending the data. So this implementation allowed us to improve in the following directions. First of all, we can do 10,000 calls per data center, which means that 10,000 threads of different tasks for processing. So having this, it's possible for us, for example, to assess to make a crop classification for the entire corn belt for the one run of the system, which takes about only 30 minutes altogether. So after 30 minutes, we know we can get the classified crops for the entire corn belt right away. Comparing to current implementation, it is like saving not hours, but days. Another one important thing for us is the cost model. So what's cool about the function as a service that we pay per run. So depending on how many runs required, how many invocations we are charged for, which makes us to align the actual cost model with the implementation model. Another one is the quick deployment. Since we are a venture-funded company, we need to grow fast, and we need to make sure that the implementation and every iteration is deployed really quickly. So, potentially, we would consider some other more in-house implementation, but currently the cloud serverless version of the infrastructure is totally fine for us. As well, it has a good login and traceability, so we can track, for example, what went wrong. And yeah, as the conclusion to how it worked for us, so really the satellite data is a fat data of about 5 petabytes, and it requires really resources, the infrastructure, and being smart about what exactly is going to be processed. So the function as a service was a good solution for us. And the Astro Digital monitoring platform is online, so we have a web browser, so you can draw an area of interest and get the series of satellite images to look at. So feel free to check out or to talk to me how to use the satellite data for different tasks. Thank you. Any questions about satellites or AWS? Yeah?
Do you assume any of the new verse that have more spectral layers?
So in addition to Landsat and Sentinel, in addition to Landsat and Sentinel, our own constellation of satellites, it has the same spectral bands to have a consistent time series, but it provides the daily monitoring. So the fleet of 10 satellites monitors the entire landmass once every day. Thank you.